In this video and in the next video, we are going to develop something that is called as a Gauss law. And Gauss law was first derived by a German mathematician called Carl Gauss. Basically, Gauss law is an observation which makes it easy to find out electric field. We saw how to find out electric field using Coulomb's law in the previous videos. And when the charge distribution is very symmetric, Gauss law makes calculations of electric field much more easier. And in this video, let's see the part 1 of the logical derivation of Gauss law. So say I have a closed surface, and by closed surface I mean a surface, a 3D surface which is in the shape of an oval, something like an egg, which is like a completely closed surface. And I have a point charge of magnitude q near it. And let us see what is the net flux through this closed surface. So to illustrate it, I have a ball of string. This is my closed surface. It really need not be a uniform surface. It can be of any size and any shape. And I have a point charge here, so my electric field lines are going to go something like that. If I have a point charge, obviously the electric field lines are going to go in this direction, emanate from it radially. Okay. So let this, I have a toothpick with a blue head, and that is denoting my electric field lines. And say I have a point charge here, so my electric field line is going to go through my surface. However, since there is no charge inside the surface, the electric field line needs to come out too. Because remember, we said that electric field lines start on a positive charge, and say my charge is placed at this point, the electric field line will start from positive charge and terminate on a negative charge. So, of course, if there is no charge inside my surface, then the line has to get out of it. Then, let me pick another one. Say it is going in this direction. Alright, and my charge is at this point, so the line enters at one point and gets out at a point. And there will be some lines which will just glance off the surface. It will be tangential to the surface. And assume that they all are starting at the same point. This is just one point, and the line is glancing off at the surface. Now, let us also mark the dA vectors which are perpendicular. Or before that, let's note one more thing, that since the electric field lines are making different angles with the surface at every point, and since the surface is not uniform and the magnitude of electric field over the surface is not uniform, we will divide it into small segments, and each segment will have its own dA. So let's see what will be the dA of this segment where the electric field line is going inside the segment, and it is going to be perpendicular, something like this. Alright, this is the dA at this point, and this is the dA at this point. And obviously dAs are perpendicular to the point at that, let me move this in the center. dAs are perpendicular to that element only, so the dAs are going to be in separate direction. And let me pick a dA for this element at which the electric field is tangential, and it is going to be something like that. Okay, so what do we see here? The electric field line is going in this direction. The tip is the arrow. The tip of my toothpick denotes the arrow. And so here the electric field is going that way, dA is in this direction. So the angle theta of the EA cos theta is greater than 90, and that means that my cos theta is going to be negative. And that means that at all the points where the electric field line is entering the surface, my flux is going to be negative, because E dA cos theta is going to be negative. Then the points at which the electric field is emerging, and this is the arrow tip, here the angle between E and dA is a positive angle, is less than 90 degrees. And so my cos theta is going to be positive, and the flux E dA cos theta is going to be a positive term. And the third thing to note is that the points at which the electric field lines are tangential to the surface, At these kind of points, my dA and electric field lines are basically perpendicular, and so the flux at that point is zero. Essentially, no electric field line is intersecting that small element. And if you look at the surface, really you can figure that for all the elements in the surface, one of these is going to be true. Either the cos theta is going to be greater than 90 and the electric field line is entering, or the electric field line is exiting and cos theta is less than 90, or the electric field line is tangential to the surface. And so I can divide my entire surface into an element which falls into one of these three types. And so let me move this, and we can say that if I divide my element, if I divide my surface into small elements like this, say these are my elements, and I'm making fairly big elements, but if I divide my surface into infinitesimally small elements, then at each point I can say that, so this electric field vector goes like that, so electric field goes like this, it goes inside this, and say it comes out of this point, and this is this line continued basically inside the surface. Similarly, there is an electric field that goes, so this one is the one that glances off, and I will show it as if it's glancing off this surface and it is tangential to this surface. And so what I can say is that I can divide my elements into three types. My dA here is like this. Let me show you. My dA is here. So dA to this surface is in this direction, dA to this surface is in this direction, and dA to this surface is perpendicular in this direction. So what do I have? What I have is theta here is 90 degrees, theta here is this, which is greater than 90 degrees, and theta here is less than 90 degrees. And so, as we just said, if we can divide our entire surface into elements, and the elements will fall into one of these categories. Theta will either be equal to 90, and my phi e, or more correctly d phi e, will be equal to 0. Theta is going to be between 0 and 90 degrees, which are elements like these. And so my d phi e is going to be positive, and theta is going to be between 90 and 180 degrees, and so my d phi e is going to be negative. Now one more thing we should note, so we have established that all the elements are going to be like that, and what we know is that my phi net is essentially the summation of phi over all these elements, and so it is integral of d phi e's. Now let us think of one more point. We said that an electric field line always originates on a positive charge and terminates on a negative charge. And so if there is no charge inside the surface, then obviously the line cannot end inside the surface. All the lines entering the surface must exit the surface so that they can go and terminate on a negative charge somewhere else. And no line actually terminates inside the surface. So we can say that if a line enters this surface at which the angle is, at which the phi is negative, the line must exit the surface so that the phi is positive. So what we can say is that this is equal to sigma, or one more thing is these are all the lines leaving the surface for which the phi is positive. And for all the lines entering the surface, my phi is negative. So we can see this as sigma of d phi e for all the elements where the line is leaving the surface minus sigma of d phi e of all the lines entering the surface. And why the minus? Because the d phi e of lines entering the surface is all going to be negative, and the summation is also going to be negative, and so we have the minus sign. And of course we ignore the elements at which the theta is 90 degrees and the line is just glancing off, because the d phi e and the summation of d phi e's over all those elements is going to be 0. Now we just said that if a line is entering the surface, that line must exit the surface. We said, when we were discussing electric flux in the last lecture, we said that the phi E over any surface is proportional to the number of lines intersecting that surface. And so I can write this, my phi net, then as being proportional to number of lines leaving the surface minus, which is this, minus the number of lines entering surface. And as we discussed, if a line is entering the surface, it must leave the surface. So the number of lines leaving the surface is equal to number of lines entering the surface. So what do we get? What we get is my phi net is equal to 0. And really, it does not matter on the shape. This could have been a square, a cuboid, a starfish, or anything. If a surface does not have a charge inside it, then the net flux over that surface is always going to be 0. So what we mean is, let me say one more point. If a surface is something like that, this is again my closed surface, I have a charge plus q here, and I have a charge plus 2q and minus 2q here. So there is some charge inside it. However, you should note that all the electric field lines starting from this plus 2q charge are going to terminate on the minus 2q charge. And so the net charge inside this surface is essentially 0. And this is an important point to note, that though we have the charge here, there is really no electric field line that will leave this surface. They will all go across the surface. They'll all terminate on minus 2q charge. And even if there is a line that leaves this surface, it is going to come back and terminate on the minus 2q charge. So essentially what matters is the net charge inside the surface. And so what we just proved is that if net charge inside a closed surface, closed is important, net is important, if surface is 0, then the phi E over the surface is also equal to 0. This is one part of the Gauss law. The second part of the Gauss law will deal with what happens when we have a net charge inside the surface, and that we'll look into in the next video.